I have a tuning fork which resonates at a frequency of 384 hertz, which is a G. And I've also got a pair of tubes. The outer tube is full of water, and the inner tube is hollow. So when I raise and lower the inner tube, I'm essentially making a musical instrument, and I'm changing how long it is. The surface of the water is the bottom of it. So my tuning fork can tell me the frequency of the sound, and if I get resonance, I also can find the length of the tube by looking at this scale. And those two pieces of data, combined with the equation V equals wavelength times frequency, they should be enough to get me the speed of sound. So that's what we're going to try to do. So I'm going to start off with this tube at around 15 centimeters. And I'll give the tuning fork a good whack. When I hold it over the tube, I don't hear anything. So I'll start increasing the height. And now I'm actually hearing something. I don't know if you can. But there's a howl when I have the tuning fork above it at this height. It's only right there. If I go higher, it goes away. If I go lower, it goes away. So when I look at it, that is 21.7 centimeters. So my length of the tube is 21.7 centimeters, which of course is 0.217 meters. So does that help me with wavelength? Well, this is a closed organ pipe. And that means that there must be a node on the bottom. There must be no motion of the air. And at the top, we need an antinode, or max motion. And you know that the smallest chunk of a wave that can fit that is the antinode, the node, and then half of a bump in there. And we've seen in class that that ends up being the length of the tube is 1/4 of a wavelength. Because a full wave is 2 bumps, 3 nodes and 2 antinodes. So what that means is that 4 times the length of this is going to be my first wavelength. So L equals, wavelength is going to be 4 times 0.217 meters. So that means my first wavelength is 0.868 meters. Okay, so we also do know the frequency, which was 384 hertz. So that means the velocity of sound must be the wavelength times the frequency. So 0.868 meters times 384 inverse seconds, or hertz. So if we do that out, we get a velocity of 333.3 meters per second. That's a little bit slower than the expected velocity of sound in air at 20 Celsius, which is about what this room is. That's usually considered to be 343 meters per second. So this would be due to a couple different things. It could have to do with atmospheric pressure. It could have to do with just experimental error. But it's a little lower than what we'd expect. So if this was the problems we were doing in class, I would then try to send in a different frequency, and we try to produce what the next standing wave is. I only have a certain number of tuning forks, and I don't have one that's twice the 384 hertz. So we can't do that. But what we can do is we can predict the length of the tube that would have the next resonance at it for this tuning fork. So that would be a much longer tube. I actually can't draw it to scale. It would be 3 times longer. And what we'd have in it would be the next possibility. So we can't have half a wavelength because that would have a node at the other end. And we can't have 2 nodes. So the next one we can do is 3/4 of a wavelength. So that would be something like this. So, in other words, it should be 3 times farther than what we currently have. So 3 times 0.217 is 0.651. Let's see if we get a resonance there. So I'll just bring my tube farther out. Should be about here. And I do. Drop it down, I lose it. Go higher, I lose it. But around 0.65,